By the autumn of 1943, the Wehrmacht's armored columns still dominated the open roads of occupied Europe. Their logistics relied on speed, coordination, and the near invulnerability of their armored spearheads. In Italy, however, a peculiar imbalance was emerging. German panzers had the firepower to repel conventional assaults, but their mobility depended on fragile supply and terrain networks, bridges, tunnels, and narrow mountain roads that made them vulnerable to unconventional disruption. It was in this context that a small Allied engineering unit stationed near Salerno began experimenting with new anti-tank triggering devices. Traditional demolitions required direct observation or contact mines. Both demanded proximity that cost lives. A junior electrical engineer attached to the Royal Engineers Field Detachment proposed a modification using telephone wire and magnetic induction. His idea was regarded as reckless, a crazy wire trick, as one officer described it. But there was no alternative that could stop tanks moving at full speed down the mountain pass without artillery support. The challenge was to detonate charges precisely beneath the lead tank, not before or after, and without being in visual range. The engineer's plan was to create a conductive loop across a narrow defile, and trigger the circuit remotely through the tank's own movement. The theory was simple. The metal chassis would bridge a hidden current field, completing the circuit and igniting the detonator. It was an electrical adaptation of an anti-vehicle mine, primitive but potentially devastating. The experiment was approved not as a strategy but as a desperate test. Materials were scavenged from communication stores, miles of copper wire, salvaged transformers, and spare blasting caps. The explosives were standard British ammonal charges, buried in a staggered pattern along a 50-meter stretch of road. On paper, it was an implausible contraption. In practice, it would become one of the first recorded uses of an electromagnetic trigger against armor. Construction began on the night of November 3, 1943. The engineers worked in near darkness, muffling tools with rags to avoid detection. The mountain road above Battipaglia curved sharply along a limestone ridge, perfect for concealment but treacherous for wiring. The design called for two conductive loops, each laid parallel across the surface, then covered with dust and debris. Between them, at precise intervals, lay three ammonal charges connected to detonators wired into the circuit. The key to the system was not the explosives, but the trigger. The engineer designed a crude transformer unit from scavenged radio parts and a bicycle generator, converting a hand-cranked current into a stable low-voltage field along the wires. It remained inactive until he closed the final relay from a hidden control post 100 meters away. When the first metal object bridged both wires, effectively shorting the field, the circuit would complete and amplify through a secondary relay, firing all charges simultaneously. Traditional demolition doctrine dismissed this approach. Electric triggers required direct connection, and magnetic influence fuses were still experimental, primarily in naval mines. Yet the principle was sound. Any conductive mass crossing a charge gap would act as a switch. The challenge lay in precision. Too much current, and the field would arc prematurely. Too little, and the signal would fail to reach the detonators. The wiring process took 6 hours. Each connection was tested by continuity meter, then reburied. Rain threatened to short the entire system, forcing the team to insulate the joints with melted candle wax and strips of tar cloth. By dawn, the setup appeared indistinguishable from untouched roadway. Only the faint metallic glint at extreme angles betrayed its existence. The engineer wrote in his log that the entire mechanism was balanced on the width of a human hair. Its success depended not on explosive yield, but on the precision of timing, an invisible field waiting for steel to pass. At 9:12 on November 4th, the Panzer column began its descent toward the pass. Recon reported a formation of 8 medium tanks, followed by supply vehicles and an engineer truck, moving in close intervals to maintain momentum on the narrow road. Visibility was limited by a low haze and the road's sinuous profile, which funneled movement through a single predictable lane, a tactical vulnerability the demolition plan had been designed to exploit. As the lead vehicle crossed the prepared zone, its steel belly bridged the two buried conductors. The short formed an immediate low-resistance path. The transformer amplifier at the control post detected the sudden change and closed the firing relay. In less than a second, the detonators received full current, and all 3 ammonal charges detonated in near simultaneity beneath the first and second axle lines. The physical result was instantaneous and brutal. The blast sheared track links and threw roadbed debris into the underside of the following tank, rupturing sponson plates and severing external fuel lines. The lead tank's suspension collapsed, its weight wedged against the road's escarpment. The second vehicle, struck by the shockwave and flying shrapnel, spun and came to rest almost broadside. Within 3 to 5 seconds, the halted lead vehicles formed an immovable barrier across the defile. Drivers in the column reacted with emergency brakes and clutching gear changes. Momentum carried some vehicles into the wreckage, creating a compact pileup. Dust and smoke filled the pass. Horns and shouted orders were lost beneath cascading metal and collapsing gearboxes. Mechanical transmissions jammed as engines stalled from track damage or from overheating caused by jammed idlers. By the 9th second, the column's forward motion had ceased entirely. 8 armored vehicles immobilized, the road blocked, and fuel and ammunition now static hazards. The tactical effect magnified immediately. Radio traffic from the column, previously steady, turned intermittent and confused. Message relays failed as antennae were damaged. Supporting elements behind the crest could not pass, creating a logistical backlog that froze reinforcements and recovery teams. Within minutes, observation posts and nearby anti-tank detachments exploited the paralysis. Pre-registered artillery fire found choke points formed by the stranded vehicles, while infantry-mounted PIAT teams advanced on the flanks now exposed by the immobilized formation. The wire trigger system had not aimed to destroy the entire column in one strike. Its design objective was temporal collapse. By converting motion into an instantaneous mechanical stop, the device achieved operational paralysis measured in seconds. The pass, once an artery for armored thrusts, became a trap whose lethality derived from timing, terrain, and the reproduction of industrial components into a single triggering field. Post-action inspection revealed that the event was not merely an explosion, but an engineered synchronization of shock, resistance, and motion. The charges had been spaced with mathematical precision, producing a concentrated pressure front that traveled laterally under the road surface. When the detonators fired, the layered gravel and clay acted as a waveguide, directing the blast upward and forward, an improvised shaped charge without any metal liner. The explosive force struck the 1st Panzer's front suspension at its weakest stress point, fracturing the torsion bar housing and deforming the hull floor. The copper wires, vaporized in microseconds, left faint parallel scorch marks on the roadbed, marking the circuit's last moment of continuity. Instrument fragments recovered from the control post indicated that the voltage spike exceeded 800 volts at detonation, a current surge amplified by the collapsing magnetic field of the transformer. The timing sequence was effectively self-correcting. Even if one detonator failed, the transient pulse would have re-triggered the secondary relay, guaranteeing total detonation. It was a system that functioned faster than any manual command could. Engineers later estimated that from the moment the lead tank's tracks made contact to the ignition of the main charge, 0.07 seconds elapsed. The shockwave reached the following vehicles before their drivers perceived the flash. Within 9 seconds of initial contact, the entire column was immobile, either disabled or obstructed by wreckage. The phenomenon was less about destruction and more about the physics of instant mechanical arrest, momentum meeting engineered resistance. German recovery teams who reached the site hours later found that the damage seemed disproportionate to the quantity of explosives used. Their reports noted unfamiliar electrical initiation, assuming a radio-controlled trap. They did not understand that the detonation had been triggered not by transmission, but by the vehicle's own mass closing an invisible loop of current. In operational terms, the result was equivalent to a minefield, an ambush, and an airstrike compressed into a single second of synchronization. Proof that precision, not quantity, could define tactical outcome. Within minutes of the detonation, the blast zone became a choke point of mechanical chaos. The narrow defile that had once enabled rapid movement now transformed into a metallic barricade. Debris from the leading tanks blocked the road entirely, while fragments from ruptured ammunition bins ignited secondary fires along the ditch. The flames consumed exposed cables, oil, and insulation, destroying any trace of the hidden wiring and masking the origin of the explosion. German command attempted to restore mobility through standard recovery procedure, detach rear vehicles, reverse the column, and clear the wreckage with engineering equipment. But on this road, there was no lateral clearance. The slope on one side and rock wall on the other left no space for bypass. The immobilized tanks became permanent obstacles. With the road impassable, supply convoys behind them halted, artillery movement ceased, and reinforcement timetables collapsed. The incident created a temporary isolation pocket stretching several kilometers. Infantry units expecting armored support found themselves exposed to counterattacks, and communication cables along the route were destroyed by the same shockwave that had torn the asphalt. For 36 hours, the entire subsector of the front froze, not through combat attrition, but by mechanical paralysis. Allied reconnaissance flights confirmed the disruption the next morning. A cluster of blackened vehicles clogging the pass, smoke plumes marking stalled convoys, and disorganized movement along secondary trails. Reports described the complete arrest of armor along Route 86, an outcome achieved without sustained engagement. The 9-second event had altered the tempo of an entire regional operation. When engineers from the Royal Engineers Detachment revisited the site 2 days later, they found the wire remnants fused into the melted tarmac. The lead charge had displaced less than 1 cubic meter of earth, yet the geometry of the road amplified its effect beyond expectation. What had begun as an experiment in circuit logic had become a demonstration of systemic vulnerability. One precision-triggered point capable of suspending an entire armored column through infrastructure, not firepower. After the engagement, Allied field engineers documented the system with unprecedented thoroughness. Every component, transformer, detonator, insulation joint was photographed, measured, and logged. The findings surprised even the ordnance experts. The principle of the wire trap was neither magical nor accidental. It was a mathematical exploitation of predictable variables: vehicle width, contact conductivity, and propagation delay. Calculations showed that the tank's chassis, with its 6-meter wheelbase and full metal track, acted as both conductor and amplifier. When it bridged the buried loops, it momentarily formed an electromagnetic bridge several thousand times more conductive than the soil itself. That brief surge activated the relay almost without measurable delay. In effect, the Panzer became the switch that destroyed it. The test report emphasized 3 factors. First, reliability. No manual intervention, no radio signal, and minimal risk of premature detonation. Second, efficiency. 3 charges totaling less than 40 kilograms of ammonal achieved results, comparable to air-dropped ordnance. Third, concealment. Unlike pressure mines, no visible trigger existed. Even trained sapper units could not identify the setup without electrical instruments. Plans were drafted to replicate the system for larger operations in northern Italy and later in France. Field manuals began including a short appendix titled Induction-Triggered Demolition Circuits, recommending its use for narrow passes, bridges, and tunnels. It became a precursor to what later engineers would describe as passive conductive detonation networks, the earliest ground-based electromagnetic triggers. However, the method's success also revealed its limits. The precise tuning required stable voltage and dry insulation. In heavy rain or variable soil, conductivity, premature shorting was inevitable. Furthermore, the copper wire needed for large-scale use was already in short supply. The system remained a specialist weapon, effective only when executed with scientific accuracy. Still, the experiment marked a turning point. For the first time, the battlefield had witnessed electricity functioning as a weaponized timing mechanism, not to transmit power, but to weaponize presence itself. The Panzer column's destruction was the prototype of a new kind of control, defeating motion through engineered anticipation. Within days, German recovery and engineering commands re-evaluated doctrine for movement through confined terrain. Immediate countermeasures included metal grid probes pushed ahead of lead vehicles, insulating mats tied under hulls, and short-range radar and radio sweeps to detect anomalous electrical fields. Sapper detachments practiced progressive clearance drills, forward reconnaissance with electrically isolated rollers, followed by remote-controlled demolition tractors to detonate suspected charges at safe distance. At the tactical level, armored formations altered intervals and column depth, adopting staggered echelons to prevent single-point blockages from halting entire formations. Commanders ordered mixed column movement, infantry and pioneers interspersed with tanks, to increase the number of bodies capable of clearing obstacles quickly. Logistics planning incorporated contingency windows for engineer recovery, reallocating support vehicles and prioritizing bridge-building units on likely choke points. Allied staff integrated the wire trigger technique into deliberate denial operations. Planners mapped terrain bottlenecks and prioritized conductive triggers, where concealment and approach predictability were assured. Coordinated actions combined passive induction traps with ambushes, pre-registered artillery, and sleeper partisan teams to exploit immobilization windows. The method's utility was greatest where geography-constrained maneuver, mountain passes, narrow bridges, and single-lane causeways. Doctrinally, the episode accelerated a subtle shift. Infrastructure became as tactically decisive as firepower. Engineering intelligence joined reconnaissance and signals as a principal axis for operational planning. Forces no longer assumed that movement equated to freedom. Movement itself could be weaponized. The 9-second halt became a case study in converting kinetic momentum into strategic vulnerability. Within weeks, the wire trigger technique proliferated across corps-level engineering units, yet diffusion revealed practical ceilings. Command endorsements accelerated production of specialized kits, pre-wound transformer blocks, insulated splice packs, and standardized detonator mounts, but supply chains strained under copper requisitions and prioritized ammunition demands. Field workshops produced dozens of viable sets, yet only a fraction were deployable where concealment and predictable traffic converged. Operational reports showed a mixed efficacy profile. In constricted mountain passes and single-lane bridges, the induction triggers delivered decisive paralysis. Immobilization rates exceeded 70% for targeted columns, and the resulting operational pauses averaged 24 to 48 hours when terrain prevented bypass. Conversely, in wide valleys or on multi-track roads, the method yielded marginal returns. Dispersed formations, wider tank spacing, and armored recovery tractors reduced both the chance of simultaneous bridging and the tactical value of a stoppage. Weather and soil conductivity proved persistent adversaries. Heavy rain, thaw cycles, and saline coastal grounds produced leakage currents that increased false triggers and premature shorting. Engineers developed improved insulation, rubberized sheets and tarred joints, and segmented circuit designs with automatic fault isolators. But these refinements raised material costs and deployment time. Where copper scarcity or rapid movement demanded immediacy, simple pressure mines or emplaced obstacles remained more practical. Intelligence exploitation amplified strategic effect. Reconnaissance mapping of enemy routes, radio intercepts showing habitual movement windows, and partisan reports on repair timetables enabled planners to maximize temporal impact. Combined operations, induction traps timed to coincide with air interdiction or artillery barrages, multiplied results. Immobilized armor became an exposed, attritable cluster rather than a single lost vehicle. Legal and ethical debates surfaced in staff correspondence. The technique blurred lines between mined warfare and booby-trapping civilian infrastructure. In areas with mixed traffic, the risk to non-combatants and recovery crews raised policy questions. Orders increasingly restricted use to clearly military roads and required post-action marking when friendly forces resumed control. Technically elegant but logistically costly, the wire trick demonstrated a recurring wartime paradox, a high payoff innovation constrained by material realities, environmental fragility, and the opponent's rapid adaptation. Its greatest contribution was conceptual, reframing mobility as a controllable resource and proving that well-timed, electrically mediated interruption could convert transient engineering ingenuity into operational advantage. After the initial wave of deployments, the wire trigger technique moved from improvised innovation to recorded procedure. Field manuals codified its parameters. Ideal choke point geometry, required insulation standards, relay and transformer specifications, and fail-safe checks to reduce fratricide. Engineering schools included classroom dissections of the Battipaglia engagement, using measured diagrams to teach timing, concealment, and integration with artillery and infantry exploitation. The method became one tool among many in deliberate denial doctrine. Operational records show its greatest value as a force multiplier in theater-level denial campaigns, rather than as a strategic weapon of attrition. When integrated with interdiction airstrikes or partisan sabotage, the immobilization of armor allowed limited Allied resources to produce amplified effects, delaying offensives, forcing redeployment of scarce engineers, and creating targets for concentrated fire. Conversely, where logistics and terrain permitted rapid clearance, the technique's effect was transient and costly in material. Innovation also drove counter-innovation. Sapper units developed non-conductive advance rollers, electromagnetic field detectors, and preemptive subsurface probes. Recovery formations introduced armored rollers and remote-controlled winches to reduce stoppage time. Intelligence units prioritized route variation and deception to deny the predictable approach geometry that the induction system required. Post-war analyses traced a lineage from these field circuits to later passive fuse research and to doctrines addressing improvised explosive initiation. Military engineering doctrine absorbed several enduring lessons: weaponize predictable movement, exploit infrastructure choke points, and treat electricity as a timing mechanism as much as a power source. Legal reviews after hostilities emphasized strict targeting controls to protect civilians and repair crews, shaping post-war rules of engagement for area denial systems. In technical histories, the wire trigger episode appears as a clear instance where small-scale electrical ingenuity translated into operational leverage. Its legacy is not a single triumph but a pattern. Precise timing, engineering discipline, and integration with combined arms planning can convert modest resources into decisive temporal effects on the battlefield. The Battipaglia episode closed as a tactical footnote and an engineering case study. A single, carefully tuned circuit had converted predictable movement into immediate paralysis. Operationally, it demonstrated a constant. When mobility depends on constrained infrastructure, precision timing can be decisive. The wire trigger did not win battles by itself. It reshaped opportunities, immobilized armor, created windows for artillery, airborne observation, and infantry assault that otherwise would not have existed. Strategic follow-through determined the method's value. Where planners paired induction triggers with reconnaissance, interdiction fires, and rapid exploitation teams, the 9-second halt produced cascading effects lasting days. Where follow-up was absent or terrain permitted bypass, the interruption was a delay easily repaired. Thus, the technique's potency derived less from novelty than from systems integration. Engineer, planner, and attacker had to operate as a coordinated chain. Material limitations and environmental fragility prevented mass adoption. Copper scarcity, wet soils, and the need for meticulous insulation constrained deployments to selected bottlenecks. Adversary adaptation. Advanced probes, insulated rollers, and altered column discipline reduced surprise. Still, the concept persisted. Electricity could be weaponized as a timing mechanism rather than merely as a detonation signal. Post-war engineering and doctrine absorbed the lesson. Passive initiation methods, remote arming protocols, and area denial principles evolved from these field experiments. Legal and ethical frameworks later circumscribed use to avoid civilian harm and to mandate markings once hostilities ended. In sum, the wire trick was neither miracle nor myth. It was an exemplar of applied physics and tactical imagination, a minimal resource, precisely deployed, producing a disproportionate operational effect by stopping motion instead of annihilating force. The 9 seconds of arrest remain a concise demonstration that control over movement can be as decisive as destructive power. If you enjoyed this video, don't forget to like, comment, and subscribe for more WW2 stories.